of starting this as not just a tech-based community, but art, science, policy, and tech, right? So that's Quantum Computing India. Now, how have we structured ourselves? Like, it has evolved over a period of time. So we have like three specific streams of engagement that we are doing, right? So the first one is knowledge series, where essentially we are doing, webinars like this, both online and offline. And then we had like a couple of professors from IISc, Indian Institute of Science in Bangalore, which is one of the premier research institutions that is doing a lot of research in quantum area as well in India. And we do podcasts, webinars. We have done a workshop as well. One new thing that we have started doing very recently, which is breaking down research papers and then like making sure that people understand, right? Like removing all the academic lingo out of this and then like bringing the knowledge to common man, right? That's whole part of the knowledge series that we are doing. The second thing that we do, which is very interesting, is the hack series. Now, since March, we have been working on something related to quantum finance. So a couple of streams that we are working on. One is volatility modeling. So if you had seen how this coronavirus and the information related to coronavirus, how is originated and how is it dissipated into the world through social media and through like traditional media, and what kind of impact it's having on the markets worldwide, right? So till now, we didn't have enough computing power to really model the information flow, right? Like we are generating petabytes of data per second, right? And we don't have enough computing power to actually model it. Like all we do is like sensitivity analysis and like, text-based classifiers and stuff like that. So now with the power of quantum, or the understanding of the quantum's power that we have, we are trying, right? Like we are still at a very early stage in terms of modeling volatility and how it impacts the capital market specifically, right? The futures and options are the first to react to any kind of news that happens around the world, right? So it makes logical sense to see what's the impact of the butterfly flapping its feathers, and then like what kind of impact it's going to have on the market, right? It's at that level. Like I said, we are in a very early stage. The second thing that we are doing is very related to this, which is options portfolio optimization, which I would say we are like 40% there. So once we started doing that, as a community, it started, right? So a bunch of us, we were having discussions in a workshop, and then one subject matter expert, he came and said, hey, can we do something related to finance using the wealth of knowledge and the kind of talent that we are having in this community? That's how it started. It literally started as a conversation. Then like we floated like a few forms, we invited people to join. And then like any community, like initial interest will be really high, like 30, 40 people were there. Then we kind of set processes around it. We were meeting every week. We were like assigning tasks, and then like it slowly dwindles down. And then like right now there are like 8 of us working like diligently on this particular problem. And one thing that we have learned here again is that hybrid computing is the way to go. You can't directly delve into quantum computing per se. So you have to do certain aspect of input feeding through your classical computing method. And then the other side happens on the quantum side, right? Like which we'll talk about in a bit. So this is the second stream of things that we do within the community, which is the hack series, right? So if anyone here, if you have an idea, if you're a subject matter expert in certain things and you think based on like our limited knowledge with respect to quantum as to how it can be applied to your industry, we can see how we can leverage our community's knowledge and the people that we have to delve or like deliberate on a solution together, right? So that's the hack series part. The third thing that we are doing is like actually building a very vibrant community, right? So the thought process here is like the space that you're building has to be safe enough space for people to feel comfortable enough to fail, right? That's very important, right? Because if you're not taking those chances, then you're not literally growing. And then especially given the fact that like we are in a very nascent kind of a technology, it's very important to create that kind of a space. And we are working on that very diligently in terms of, making sure our communications are set right. We are like open to everyone, open to different types of perspectives, and not excluding anyone at the end of the day. And when I say anyone, anyone's opinion, right? Then the biggest strength of a community is that, like, usually when we start learning something, there are like different types of people. Like certain people are very diligent, like they can go on, and then they can go deeper into learning something new. But most of us need a support structure, right? And that's what we are trying to build, which is, hey, if you're trying to learn this on your own, probably 1 month, 2 months down the line, you're going to lose interest, right? But when you're part of a community, then like these things happen, right? So when someone is not coming for the next event, he'll be like, hey, bro, what happened to you? Why didn't you come, right? Or like we bring in this new problem that we are trying to solve as a community together, right? So that we have seen that work quite well in terms of prolonged learning, right? So these are the three things that we are trying to do: the knowledge series part, the hack series part, and like consciously building a very vibrant community. So that's the intro about Quantum Computing India per se as to what we do. Now we are going to delve into quantum computing for beginners, and the agenda is very simple. We break it down like we keep saying, it's for beginners. So we are going to break it down into like what is quantum. We start at that level. Then we go into what is computing. Then we kind of look at why do we even need quantum computing at this stage in the world, in the current world. And then we kind of delve into the theory part that has kind of accelerated this development. Who are all the people behind those theories, like the quantum theory aspect of that. And then we get into the main concepts like superposition, and then like don't worry about like terms that are being thrown around over here. You'll keep learning, like if you keep coming to our events, these are things that just become a second nature to you, right? So KG, Karthik, Ganesh, and I will be taking this session, and then we'll have a small Q&A, a small break, and then we'll delve into Qiskit, so which is a simulation thing through IBM. So it's a full-on platform. So you have a hardware level, you have a software level. Even in software level, if you're like working at a circuitry level, so that will do from let's say 510 to 6 is what that is scheduled, right? Okay. So with that as the intro. So till now, do you guys have any questions, any thoughts? Take like a 1 minute break. All right. Cool. So what is quantum, right? So for the longest period of time, we all know that the universe is made up of energy and matter, right? And we all know that matter is something that you can see. You can like look at it in discrete units, right? Like, you can go all the way down to atoms and electrons, protons. And then if you believe in string theory, you are like thinking about quarks and like the frequency at which the strings are vibrating and stuff like that, right? Which are discrete units. But energy was always considered as a waveform till 1900s, when Max Planck came out with this paper where he was like clearly able to show that energy also exists as discrete units, discrete as in like individual packets. Now these individual packets of energy are called quanta, right? So from there comes the term quantum. We'll get into the bits and qubits part. Almost everyone would have heard about that. We'll get into that at a different, right? So Max Planck, like I said, so in 1900, he releases this paper, energy exists as individual units. That's called quanta, and he got the Nobel Prize for that. And Albert Einstein, right, like who's known for his relativity, actually got the Nobel Prize for something else, which is discovery of the law of photoelectric effect, right? Which is how do you make this movement of quanta and then make sure that they're conducting electricity, right? Like I'm like abstracting it down to a very simpler terms, but at a very high level, that's what it is, right? So these kind of set the base for this quantum theory to take off, right? And we'll talk about how people built on that in the future slides. Okay. So now, so we say this quanta, right? So what are the big tenets of this theory? Any theory comes about with like certain type of hypothesis. Someone is coming and like doing research on that and kind of validating that, right? So the first one, like we talked about, is energy exists in discrete units, right? Individual units, which is quanta. The second thing is elementary particles, depending on the condition, may either behave as particles or waves, right? Which is the duality aspect of that. So like at some points it's acting as a waveform, and at some point it's acting as individual unit. That's based on the conditions in which it's thriving, right? A third important aspect is the movement is inherently random, in the sense, like if there's a quanta at this stage, you really don't know at what direction it's going to go next, right? It's completely random. Like no matter how much time you observe it, you'll try to get out some kind of frequency out of it, but that's because you're observing. But when you're not observing, it's totally different. Like there's no probabilistic way to determine in what direction this next quanta is, like in which direction it's going to go, right? So KG has a very interesting experiment where he'll like show this. Then the fourth important aspect is, tied to something called the spooky action at a distance, right? The simultaneous measurement of two complementary values. So let's say a quanta that created at the same time, right? If two quanta are created at the same time, though they are at a very long distance sets apart, but the important aspect is they should be created at the same time, right? So when you measure the one thing, then the other thing goes for a toss. Or if you measure this, it can be looked at it in two ways, right? So if you measure this, the other thing goes for a toss. Or the other thing is, measure this, you can find the value of the other thing as well. Again, that will delve mathematically, it'll make more sense. Now, okay, so this we kind of talked about now, which is the superposition part, right? So this is a nice gist that kind of captures this whole point, right? When no one is observing, the skater can be at any point in space, right? But the moment you observe, like he's gonna stop somewhere, right? That's what essentially superposition is, right? So when you bring it down to at a quanta level, what it means is when you're not looking, you don't know what these quantas are doing, but then when you observe it, it's gonna like give you one output, which is the core principle behind qubit as well, right? Now, the second part, which is what this I just talked about, which is quantum entanglement. Now, in quantum entanglement, so the two quantum particles created together are entangled, right? So now this is a concept like which was a little mind-bending when we started, because at least I didn't really understand that part, but the time becomes very important here. So that's why if you see the y-axis, it's time, and the x-axis is space, right? Yeah, Ashish will answer those questions. So there are ways to measure these things. KG will take us through that. So the two quantum particles created together are entangled, right? So the time becomes very important over here. Now, that's why the polarization of this thing will be connected no matter what the distance is between these two things, right? Now, like there are like Chinese companies that are trying to use this to, encrypt data as well using this, which is a very profitable field. All right. So now, like a little physics behind that, if you want to understand that, it essentially happens because the time becomes very important because, in Einstein's space-time continuum, which is a curve, like every incremental radius, the times remains the same, right? Like that's why the space increases, but the particles created together, that's very important. Just keep that in mind, because when you're like coding, that's going to become very important. So this is also called, so the colloquial term for that is long distance telepathy or spooky action at a distance. All right, that's entanglement. So basically two things tied to it, like think of it like a soulmate, right? They're somewhere there, and then like if she sneezes and then like you can feel it, that's the easy way to understand, right? All right, so now now that we have like talked a little bit about quanta, right? Quantum, the discrete energy unit. So what is computing? Now, the computing part has the goal-oriented task, right? So if there's a process, computing is the process of using technology to complete a given goal-oriented task, right? So that's why like computer algorithms are like deterministic, right? Like most of the time, you know what the output is. Like if you follow the algorithm in a way that it's to be followed, you know what the output is. Whereas like talking to a human being is very different, right? Like I'm sitting here, you guys are sitting on the other side, and then like those you're sitting and nodding, like probably you're thinking about something else, right? Whereas computers are always like you give the input, you follow the process that you're supposed to follow, you know what the output is going to be. Unless you're doing some machine learning things, we'll get to that at a later stage, not too confused right now. All right, so then any machine that does this is a computer, right? So why the need, right? So why are we talking about, so, we have enough, right? Like I'm sitting here talking and it's getting this webcam is capturing this, converting it into a digital signal, and then it's sending it through some fiber optic cable, and then it's like getting streamed into your computer, and then like you are able to see it, right? We have already achieved so much. So why this quantum computing becomes important is the next thing that we talk about, right? So for that, we have to understand what computers are made of, right? At the very base level, it has very simple three things, right? It has a memory which stores these bits, an arithmetic unit which is just going to do addition, subtraction, and if you're able to do addition, subtraction, then you're able to do multiplication. Then essentially all other operators are a combination of these three things, right? Now, the logic that controls these three arithmetic operations is the control unit. That's it. That's what makes a computer, right? Anything that we do, it can be done, like if you break it down to the most singular level, it can be done by a LKG student, like a kindergarten student, right? Because it's going to be at that level. It's going to be either 0 plus 1 is 1 or 0 into 0 is 0. It's going to be at that basic level. But it's just that it does it at a faster rate, that it feels like a million kindergarten students are sitting inside your computer and doing these operations based on certain logic that's given by the control unit, right? That's the part, right? Now, what is making this possible, right? So the computer has the chips, the chip has a module, the module has gates, and the gate in turn has transistor, okay? Now, the reason why we're talking about this is because the important point, if you see, the core point is what? It's the transistor, right? Now, the transistor is what is gonna create a bit in your computer, right? So you see that finger over there at the transistor part. There's a picture of that. Okay. Let me just come. Yes, right? So now what it's actually doing is, if you let the electrons pass through, right, then it becomes high charge, and that's called a bit 1, right? And when you're stopping the electron flow, the dots that you're seeing over there are the electron flows, right? Now, if you stop that, it's low charge, it's 0. At a very, very fundamental level, that's what is happening. When we say classical computers have bits and quantum computers have qubits, we have to understand this, because bit is nothing but letting electrons flow because of that's what the property of a transistor is, right? And then if you don't allow the electrons to flow, then it's a low charge, so it's 0. So that's 0 and 1. That's the most fundamental level to which classical computing can go, right? Now, so to arrive at this, okay, to arrive at this 0 and 1, the number of electrons needed is what is represented over here, right? If you have a football field, a digital computer, a classical computer uses thousands of electrons to represent 1 or 0, right? And whereas a qubit, which is in a quantum computer, it just uses 1, right? Because it uses the spin position. Again, KG is going to explain that. I'm just like giving an overall view over here, okay? Now, why this becomes important is because quantum is the way in which nature processes, right? If mathematics is the language of nature, then the computing part is happening at a quantum level, right? Quantum computing is what nature does, right? For example, if you take the leaf, right? A photon falls on the leaf. We all know what a leaf does, right? It converts sunlight into oxygen for the plant to feed and it to grow, right? So what's happening is that the photon falls on a leaf, and then the photon, for us to take the most optimal path, it uses quantum computing, right? It's just mind blowing when they first heard it, right? Because like the kind of algorithms that we use, right, like the traveling salesman and stuff like that, which is to find out the most optimal path. Nature has solved that like long time back, and we are yet to figure that out, right? We have just termed it. We still haven't like really simulated that, I would say, right? So uh, the reason why I'm saying this is because it takes very limited energy, right? It takes very limited energy to actually do a quantum. I'm not talking about running a quantum computer, but like for you to do a computational level energy, if you calculate, this is like a fraction, right? Because what you're seeing on your screen, right? Because we are able to manipulate an electron at that level, that the computational resource that's required drastically reduces, right? So in other sense, if I take 100 steps to reach a particular solution, in quantum computer, I would have taken square root of 100, which is 10 steps, right? Square root of n. So now think about it at an exponential rate, right? So if instead of taking 100 steps, I take 10. So instead of taking 10,000 steps, I'm going to take just 100 steps, right? So that has insane implications. Now, if you think about applying that to cryptography, right? If I have to take, let's say, a SHA-256 algorithm, which is what Bitcoin uses, and a classical computer would take, that this is the typical answer that Bitcoiners give, right? Like you would need 51% of Earth's computing power, the current classical computing power, to break the Bitcoin blockchain, right? But then if quantum really kicks in, if it becomes accessible, and then it's going to take a matter of minutes for us to break that algorithm, right? This all happens because of this, what you're seeing on a computer, right? Because at a very fundamental level, one, the resource required is minimal, and you can like literally do parallel processing, right? What we didn't do or see in classical computer is really not parallel processing. It's just like different threads of processing that are happening in your OS that's switching really fast, that we don't know that we are doing only one thing at a time, right? Though it feels like multitasking. Anyway, too much time on this. I'm going to move on to the next one. All right. So what's the importance of a bit? Like we all know this. So it's a store of value. So if you have 2 bits, it's 7 bits, it's 128 different ASCII characters can be stored. RAM addresses, right? So what did we see? So a computer has not just storage, but it also has arithmetic and the control unit, right? So that's where transistors and gates come in, right? Yes. Yeah, so we'll talk about the applications of that. It's not just cryptography, it's used in simulations, drug things. Yeah, we'll talk about that. Right, so just a recap of what we saw, right? So the chips have modules have logic gates, and gates are made up of transistors, right? Now, why are we talking about this? The transistor size has been reducing, right? That's what Moore's law is, right? The number of transistors in IC doubles every 2 years, which means we have gone to the level of 14 nanometers, right? A transistor has come to the level of few atoms, the size of few atoms, right? Now you think about this, what did a transistor do? It's just like controlling, regulating the flow of electrons, right? That's what we'll see next. So transistor, which is 14 nanometer, if you compare it with the size of a HIV, right, the human immunodeficiency virus, it's 120 nanometer. So it's smaller. The current transistors that are inside your Intel chipsets that we have are like 500 times less than that, right? And the HIV itself is, red blood cell, the red blood cell that we have in our body, that's 7 micrometer, right? So what I'm trying to say is transistors have gone to the level of few atoms, right? So what's the implication of this? The implication of this is that you won't be able to control the electrons anymore, right? Because at that smaller level, subatomic level, the classical physics goes for a toss and quantum physics kicks in, right? Which means superposition kicks in, right? Which means, so what has happened here is when the transistor says no, right? Like you can't pass through, which means I'm trying to create a 0 bit, right? But the electron is not listening to that because the transistor has become really, really small. So then now the electron will just like disappear here and appear on the other side, right? Through something called quantum annealing. Okay. Now, so we have reached the physical limitation of, chunking in more transistors into a chipset, right? Which means we have reached the limitation of the maximum number of computations that we can do, right? So that's the problem in which classical computer is stuck, right? So if you have to increase our capabilities, if you have to increase our computational capabilities, then something else has to happen, which means we have to understand at subatomic level how these things work, right? Then we can manipulate that, and then we can create new types of bits. That's where qubits come in, right? So the solution is qubits, and instead of normal transistor-based gates, you will have quantum gates, right? So now that I've set the problem, I'm going to ask KG to take over from here and take us through the quantum computer part of things. All right? I hope that was clear.
Hi Sam. Hi team. Thanks for all joining Saturday 4 p.m. Great. And Sam thought that all bald haired people are brilliant and intelligent. So he threw me a problem. What is the solution for qubit, or how to stop or how to make the electron to listen to us at subatomic level? That is the question Sam threw at me. Hey KG, I want my electron at subatomic level to listen to me. At subatomic level, the electrons, not electrons, there is only one electron. It is technically called SET, single electron transistor. So when a single electron behaves as a transistor, what is 0, what is 1? Let us think about this one. I want to show one small thing. Imagine that the electron is a small ball. Assume that the electron is a small ball, one electron. What is inside this ball, or what is inside this electron? At above atomic level or beyond a normal level, there is nothing inside electron. But at subatomic level, we have many particles, and those particles have some energy. That energy is called spin energy. At some point of time, I put a ballrest in this ball. You can listen. There is a sound, right? At one point of time, the spin energy inside the electron will be at the south pole. At some point of time, it may be in the north pole, which indicates 0 or 1. Are we good now? We can represent 0 or 1 here. But there is one more situation. When this electron got ignited like this, we don't know where is the spin energy inside the electrons. Can anybody predict? Cannot, right? Which means the spin energy inside this electron has somewhere else, rotating somewhere else. That is the thing, the problematic thing, what scientific and physicists and electronics consider that this is a problem. It is called anomaly at subatomic level. And there is one more challenge also. Can you go to the next one? And here, because of this 0 or 1 or in between, which is called coherent superposition, which is called 1 and 0 position. So an electron, a single electron transistor, can be either in 0 or 1 or 1 and 0, like this. So this 1 and 0, which was considered to be anomaly, has a processing capability in different kind of mathematics model that I will cover in later. Now I want to move to next step. Here the internal position, when the electron in this excited position, or it's called electron in a coherent position, in a coherent position, can entangle with the similar property electron which are called entangled, which means this electron position, either 0 position or higher position, will affect nearest electron, or it, once it is entangled, they will represent from the anywhere else. I want to show you one thing. I'm not intelligent, so I always prefer to use simple items. Imagine that this is a rope. This one knot indicates one bit, and this is another bit, and another bit. And here I have a bit, multiple bits in one place. This bit is entangled. So there are two knots. This knot entangled with another knot. Now, if I want to process one knot, I can't do, because these two knots are entangled. Now imagine that I cut this knot at exact symmetrical position. Now it is entangled qubit. Even if I move somewhere distance, still they are same entangled qubits. And still I move apart, still they are entangled. If I keep those off bits into one portion of Earth, another portion of Earth, still they are entangled. They mimic their behavior. These two properties, which are called quantum computing properties, were considered to be anomaly. So the industry was not able to process. How can I process this? What is Sam? I am not seeing the.
Yeah, one.
I'm seeing the images of all participants.
Right. One second. Pradeep, can you give me sharing access?
So because of these two properties, coherent superposition and entanglement, scientists thought that we cannot build a processing unit or computing device at the subatomic level. But here comes a help from mathematics. There is a branch of mathematics called functional analysis, which operates on Hilbert space with complex numbers. So there is a question, how atoms can communicate in the entangled. So still that theory is under study for proof, but mathematically it is a adjoint of a number can be represented or can be mimic the behavior of the source number. If you have two matrix, the adjoint of matrix can mimic the other matrix. That is the mathematical foundation for this measurement. We will cover those things in the advanced session. We have advanced session. Those sessions exclusively cover for this kind of information. Can you go to next slide, Sam? Okay, so now the scientific community found a solution to build a computing device by embracing those quantum anomalies. So what will be the characteristics of a quantum computer if you are going to build? The size will be nanometer scale, because we are using single electron transistor. And as Sam already pointed out, they will consume very, very less energy. Remember the football ground example shown by Sam. There is only one single football, which is going to represent 1 and 0 or 1 or 0. That will cost you very less power. And the processing will be in teraflops, because quantum computers are using entirely different kind of mathematical model. They are not based out of our standard mathematics, which is based on Boolean algebra. Here you can see it is using coherent superposition, and they are operating on Hilbert space. The Hilbert space causing the power of parallel processing at teraflop speed. Can you go to next? This one very interesting to know. You see this slide, what you are seeing now. Whenever we know computing, we know AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate, right? But in quantum computing, we have X gate, Z gate, H gate. What is X gate? I want to come back to the electron ball, the ball with electron. If the ball moves this one, that can be X gate. If it is this direction, Y gate, Z gate. And it is in rotating with energies different uncontrollably. It can be anything, which is called Hadamard gate. You can see the formula: alpha plus beta 0 ket plus alpha minus beta 1 ket. the ket and then divided by square root of 2. No worries. It will be very confusing. Sam, can you go to the next slide? I want to show an interesting slide to our viewers. See, any processing or any computing must have a strong mathematical foundation. Without a strong mathematical foundation, we cannot build any computing device. So classical computers, all of you knows that classical computer using Boolean algebra, and it uses binary numbers. All the operations are in metric space. But when you come to quantum computing, it is all linear algebra and complex numbers. That's why you are seeing alpha plus beta 0 ket plus alpha minus 1 beta ket. Sorry, beta 1 ket. And these are all operating Hilbert space. You may wonder, what is this Hilbert space? KG is repeatedly telling Hilbert space, Hilbert space. Whether Hilbert is KG friend, he is repeatedly calling his name. No. Hilbert lived in the year 17th century, and his student found out this space. They named it Hilbert space in recognition to as a respect to their teacher. A Hilbert space with a n-dimensional space which can mimic the properties at the property of multifaceted, meaning that you might have been knowing that this polymorphism kind of thing. For example, red label. It is a example for polymorphism. When father asks, the son asks, quarter or half. When the mother tells, tea or half kilo or kal kilo. Because red label may be tea powder or wine. So this is polymorphism. Like that, a Hilbert space with one single word, it can give multiple meanings. Or one single operation can behave differently. So this gives the power. Actually, you need not to do anything. Within the electronics ball, single electron transistor, you read from different angle to get a different meaning. That is how the parallelism helps to build a computing device. Sam, can you go to the next one? I don't want to bombard us. This is, I like this quote by Richard Feynman, who is a Nobel laureate 1965. So far, based on our discussion, you might have think, what is this quantum mechanics? We are not able to understand anything. He is telling quantum coherent superposition, entangled, and this is used to perform calculations. If you think you understand quantum mechanics, think about Richard Feynman. He himself told, there's a question from Ashish, but when atoms are earth apart from each other, how do are still entangled with each other? Because the entangle, I will come to this question after the end of this session. The entanglement still in the research, infancy of the research stage. I cannot give you a concrete answer, but the entangled photons behave similarity in their coherent superposition. That is the answer for the time being. We will discuss in detail either offline or at the end of the session. Considering the interest of all attendees, I will move to next session. Next slide. Sam, can you go to next slide? Now, after hearing all this story and even a claim by Richard Feynman that I don't understand quantum mechanics, you want to see something practical. Okay, KG, is there any practical solution for quantum computer? Yes, there are few quantum computers in the world. One is built by IBM, other one is recently built by Google, and there is another quantum computer by Rigetti. But all those processing elements, there are multiple candidates which behave that coherent superposition and entanglement. Coherent superposition means they are there, they are present, not present, they are both present and not present, like a Schrodinger cat. You can see here in this blue screen, there is this is a diamond, there is an impurity inside the diamond. Inside the cavity, the nitrogen atom can present and also cannot present. These kind of behavior can be used for building a qubit. You can there see there are a lot of things, optical lattices, quantum lat, but I like this diamond based quantum computer. A diamond based, we all know that the diamond is a kind of carbon. Within that carbon there will be a gap. Some of the carbon you can see here in the diamond, there is a place where the carbon molecule or carbon atom is missing. That cavity can be used for build a quantum bit or qubit. And I can talk about all these things considering the time interest. I'm just leaving to your research. Now I'm moving to the next slide. Okay, now here the story goes like this. We have quantum concepts supported by mathematical foundation Hilbert space, and we have supporting physics uh, candidates which can be used to build qubits. Okay, we have built a quantum bit. What can we do? These are the things. Quantum, it can be considered into your two branches: quantum computation, quantum information. For your information, I'm specifically focusing quantum computing, but quantum physics and quantum mechanics have a lot of other applications also that which will be covered later. But here I'm covering computing related thing. And quantum cryptography, information theory, quantum error correction, and gate based computation, annealing based computation, adiabatic computation. All these things are helping us to build a production quality working quantum computers. Using these principles, IBM, Google, Rigetti, D-Wave, Alibaba, Baidu, these are all the companies who have built their own quantum computers. Sam, can you go to the next slide? I just want to show an interesting topic for our viewers. Now this is the question, right? Okay, KG, you have told a lot of stories where the quantum computing can be used. First one is searching. All of us experienced Google search. We go there, we enter, then it is giving the result immediately. Imagine that it is taking 4 to 5 seconds to return one result. When you hear, it seems to be very small time, but when you experience, it will look like eternity, even 5 seconds to 6 seconds when you are searching. And similarly, if you are using quantum computing, the searching time can be reduced to log n. The time can be reduced to very short due to the algorithm provided by Low-Grover searching algorithm. And there is cryptography. Cryptography is the first application which made the industry, the world, to turn their eyes towards quantum computing. You know, we are all using ATM card. We are very confident that our ATM pin cannot be broken. That is the reason why we are confidently taking out ATM card and then insert into your ATM machine and draw money. Imagine that somebody can break your ATM pin. Will we use confidently? A quantum computer can break your ATM pin within 4 to 5 minutes. But in current classical computers cannot break those numbers within the known period of the earth. The reason behind this one is a very large integer number. Factorizing a very large 4028 bits integer is a humongous task. It cannot be done with the known time. That is the reason why our current RSA or any other cryptography are providing security for us. But quantum processing can break that with the help of algorithm given by the famous Peter Shor from MIT. He is our guru. He is our how to say our icon. And you can create new medicines using quantum simulations. And you can even create a new particles using, because the quantum simulation is happening at the subatomic level. By manipulating the electrons, you can create new combination of particles. This is being research. This research is being done by NASA to create new particles for space expedition or ISS or travel or transport, all those things. And the very interesting part is finance. We are building, as Sam pointed out, we are building a quantum finance for building an option price prediction, which will going to give us a accurate prediction. At least we are believing. And next one is my own field. I am a data scientist who are building a machine learning algorithms. For us, quantum machine learning is going to help us to build a practically algorithm which can predict unpredictable things. And it is really very interesting to know how quantum computing can augment or complement our existing digital computer machine learning algorithms. Sam, can we move to the next one? And here I invite Sam to continue with the timeline and quantum computer. Sam, can you take? So this is the history is very, very interesting to Sam. You're in mute. Yeah. Yes,
Oh,
Sam, please take it.
okay, cool. Well, this is just a timeline of how the quantum computers and the base for that was put up, right? Like we initially talked about, Max Planck laid the foundations for all these things, and then in 1926, John von Neumann talked about Hilbert space, and then that's like KG's most favorite word. Then the quantum theory per se, right? Like when Max Planck put out that paper, he didn't really call it a quantum theory. So someone had to like really come and put it all together. Like in economics, you have like neoclassical economics, which is just like a synthesis of all the different thought process that has happened till that point in time, right? So collating all these things and then started something called a quantum theory. And Feynman, we all know, he kind of brought together the mathematical part of these things. One second. Huh. So quantum computation, essentially, I mean, that's precisely why we call him the father for quantum computation. Uh, uh, then quantum gates came into picture because like we saw, you really need, so like single electron transistors are fine, but for you to like really get to the next level of computation, you need gates, right? So quantum gates was another breakthrough. Then came David Deutsch, started with the universal quantum computer in 85, then Shaw's algorithm, which, the encryption part that KG was talking about, which is a very interesting thing. Like if you have to take one thing out of this whole thing, like I'm more interested in the quantum cryptography part of things. So this is a thing that you should be exploring if you're interested in that as well. Then Grover's algorithm talks about quantum search, like KG was saying. So if Google has to search for a particular page, like technically what it's doing is it's structuring the World Wide Web in a way that Google's algorithm can find a result for you, right? That's why you have this whole concept of search engine optimization, which essentially came out of the fact that Google's algorithm works certain way. So let me now go and create my website in such a way that I can come up on the first page of Google, right? That's really not the way it should work, right? If my information is not structured, right? Like in your brain, information is not structured. It's a network thought is what we have in our brain, right? If you really have to search something like that, then like Google's algorithm cannot work, right? So you really need, like we talked about that photon falling on a leaf and finding the most optimal path to go to the next atom, which requires that photon, right? So it should be at that level. So that's what Grover came up with. Then the first computer in 2000, then D-Wave, which is this Canadian company. This is a quantum annealer, the 28 qubit thing. Then the single electron transistor. So this is very interesting because I mean, though we all know about IBM's quantum computer and like how you need this super cooled liquid and stuff like that for your computers to work, quantum computers to work. So when we had this professor from IISc, like we came to know that there are researches that are happening in Australia. I mean, there's someone from Australia as well. They can corroborate on this, which is like their whole research, like entire Australian quantum research community is focused on creating quantum computers or creating qubits just out of silicon, right? Because you already have this existing wealth of hardware in everyone's hand. So if you can really create a qubit out of silicon, then that will like retrofit into the existing computer, probably, right? So that's something that Australia has really bet on, right? And not just that, like in IISc, our professors are working on like man-made protons, right? Like artificial protons. And then, so if you're able to create artificial protons, then how do you use that to create a computer out of that, right? So let's not just limit ourselves to the IBM version of quantum computer. There are other researchers that are happening out in the world as well. So just be aware of that. Flip-flop qubit, yeah. Silicon atom and a nest of phosphorus. Yes, see. Yeah, so once I finish this, probably Iman can talk about that. All right, so then Microsoft came out with this whole Q-sharp, then Google's Bristlebone, and then like now we know that they claim that they reached quantum supremacy. And in 2019, IBM has gotten into quantum risk assessment as well. So that's a brief history of how these things are happening. Now, this is what I was talking about, the IBM Q systems. So at the room temperature, your microwave electronics works like this, the one on the left that you see. On the right is what you have to cool the qubits to 20 microkelvin, right? To the right corner, you see chip with superconducting qubits and resonators, and PCB with a qubit chip. I mean, we don't have to really understand all these things unless you are at a chip making level of quantum, right? Right now, at least in our community, we are still at an application layer level, right? So we are trying to use these simulations and use these computers, leverage that, and then run the algorithms that are compatible with these things. And that itself is taking so much time, right? Like we started in March and we have like probably reached like 30% of what we want to really achieve through quantum finance. All right. What's next one? Okay, so that's it. All right, so that's it from our side. Did we miss anything, KG? No. Okay.
We covered everything. Now
Yeah.
we are open for
Question.
Q&A till Sadap is getting ready with workshop.
Yeah, Shadab is here. Yeah, we have a good 5 to 10 minutes to answer your questions.
Yeah,
Search
KG ready?
engine, machine learning, finance and business ops, materials and particles. So the drug simulations is another very, 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 very important area. Like given the current scenario, you know, like COVID, and you want to develop a vaccine, like the fastest way that you can simulate a drug and then like release a vaccine. Like imagine if you have a quantum computer, like this would have taken like probably less than a week's time for us to arrive at that, right? So drug testing is another very important thing, but yeah.
Unfortunately, we don't have any production quality quantum computer in the world now.
Right.
Yeah, if maybe 128 or 256 qubit quantum computer can provide a solution, but currently we have 7 qubit, and then 47 qubit quantum computer is the latest achievement by Google. But that is also not enough for
Correct. That's what they're claiming,
real-time.
so that's another thing.
Yeah.
All right, so Iman, I'm hoping that I'm pronouncing your name right. So do you want to talk about this silica atom? Because that's something that we don't really hear often in the mainstream media, given the fact that everything is like poised towards the West, and we talk a lot about this super cool qubits and stuff like that. Australia has been doing some great stuff in that aspect.
Yes, well said, Moses. It's out of University New South Wales, under the leadership of Professor Michelle Simmons.
Okay.
She's, in fact, she was Australian of the Year 2 years ago. So it's great to see that happening. And yet, basically, it's a case of using. It's just a different way of isolating the atom. So it's basically an atom of silicon in phosphorus, so that we can manipulate the actual atom. And then, like KG was saying, once you've got that, you can then use, you've got then the fact that you can manipulate it, because you can manipulate you can refer to any part of the block sphere.
Right. Okay.
So yeah, it's just another way of doing it. But the important part, which I think you alluded to, is that we know silicon very well. We have a supply chain.
Yeah.
We know everything, so we could get to market quicker,
Correct.
which is an important point. So thank you for that.
All right. Thank you. Yeah, so these are things that we get to know during these podcast sessions. Like it's, one thing to learn the tech part of things, and the other thing to keep tab of what's happening on the research side. So, so you are a little more broader level of knowledge. And then like when, if suddenly then silicon thing takes off, then you have a competitive advantage over your competitors, right? All right, cool. So it's 5:02, and Shadab, are you ready?
Yes, ma'am, I can start.
All right, cool.
Yeah.
I'll share the screen, or you wanna?
I will share, that's fine.
Share. Shadab, a quick intro about you, and then yeah.
Sure.
Hmm.
So basically, I'm Shadab, and right now I'm working as a data scientist for a startup. And our common interest on quantum computing has what brought us together to start this quantum computing India community. And I'm thankful to Sam and KG who gave it a vision, and now we are at this level. So I mean, from my college only, I was interested in doing something good in tech. From where I started data science, AI, ML, and then now currently in QC.
Cool. Awesome. Yeah.
So
Shadab,
yes, KG.
I said welcome. Go ahead. Thank you.
Yeah, thanks, KG. Okay, so I will start with today's presentation. So I'm going to introduce you all to the introduction to Qiskit. So I don't know how many of you are aware about Qiskit and how many of you have coded on it. And I'm sure many of you have used and have programmed something on quantum computers. So the agenda for today will be like, I will introduce you to the Qiskit framework that is developed by IBM. And then after that, we will talk about the environment which we need to set up locally on our system to run the code on quantum computers. And after that, we will see how to get the API access token and what are the different elements of Qiskit. And then we will implement some of the basic programming on the quantum computer, and we will try running it on simulators as well as actual quantum computers. Okay. So just to start with, KG has already covered this IBM Q systems and how these chips are getting stored and at what temperature. You can see how this complex, what level of minimum cooling temperature we need to keep to make the superposition entanglement happen on quantum computers. And these are the few of the properties of quantum mechanics like superposition, entanglement, and inference. Just to give an overview, like superposition is something like you can see if we take this analogy of, if we play two musical notes at once, and what we will be hearing is a superposition of the two notes. The same way, like if we are tossing a coin, then for the moment it is in the air, it will be in the superposition. It will be, it will be rotating at, it will be either head or tail. It can be the case. Now, entanglement is something when whatever is happening with a particular matter in the environment, the same behavior is mimicked by the another atomic particle. So this is how we can depict it. And next is inference. So inference also we all are aware of. So to mimic entanglement, we need a really high computation, and which was not possible doing on the classical resources, because of which we went to process such computation on the quantum computers. And this is the only way using which we can mimic entanglement in the real time. So IBM has already developed the quantum computers, and they have developed recently, I think, a 50 qubit system. That is very huge for the computing exponentially. So this is one of the representation of a quantum bit. So we all are aware of classical bits, which is in the form of 0 or 1. But quantum bits are something which can be 0 or 1, or which can be both. So to represent a quantum bit, it is given by the formula like alpha of 0 kit plus beta of 1 kit. And this we can see in the blocksphere here, like how it is being denoted. Okay, so coming to the next, from bits to qubits, the journey was like, if we have to process something in classical computers, obviously, since we have the information available in only form of 0 or 1 bits, that will cost exponentially very much to us. And there are certain problems which we cannot solve on the classical computers, if we say. Okay, so few of the properties that make quantum computing different are like superposition, entanglement, reverse computing, and privacy. So as Sam was telling, like he's more interested in quantum computing part of application of cryptography. So if these things will be live, I mean, these things will be live in the production in the environment, then whatever existing RSA tokens are there, that can be easily broken down using the quantum computers, and everything on the internet which is secured right now will be at stake. So we need to come up with something which can secure such things, the encryption part, and that's why the major area which we are seeing in quantum computers emerging is of the cryptography. And some of the quantum algorithms which are getting used, I mean, commonly used are like Shor's factorization algorithm, Grover's Dash, and then reducing the noise level on the quantum computers and optimizing the algos. I mean, there are various sectors in which researches are going on, and they are, and still we are not that much close to an elegant quantum computer, but people are working on to improvise noise level and to optimize the algos which are running on the quantum computers. So, I mean, few of the major problems which are there with the which are existing, like it was very difficult to build and retain qubits due to coherence, and whenever you are passing some of the inputs to the quantum computer, the amount of noise which will be existing in the environment, that affects the output which we will be getting. So that is where the NISQ area comes in the picture, where people are researching about. And algorithms like Shor's were not implemented, and then the hardwares had the constant before, like there are some pros and cons with those hardwares which are getting used. Then data storage, then the way we are passing the information to the quantum computers, and I mean, basically to process any of the information on quantum computers, we need to design a circuit for that in Qiskit framework, and then we need to implement that program, and then it will be running. So all these were a few of the problems which some of them have been overcome, and for some of them it keeps improving day by day with the researches are happening. So when we take quantum mechanics, it gets divided into two parts. One is quantum computation, where applying the gate logics and quantum annealing come in the picture. And another part of it is quantum information, where we deal with the cryptography, information theory, or implementing machine learning algos on the quantum computer, such things. So this is how we can categorize each functionality of the quantum computer, and we can analyze like how it will be working. So to go forward, before jumping to the Qiskit directly, I will give you an overview of the few of the gates, like I mean, which are commonly used, and these are not the just gate; there are many more, which we can explore later on in coming sessions. But for this session, I have just kept 4 gates to just give a touch base, and these are very important to know. So coming to the poly X gate, X gate is similar to the NOT gate, which flips the qubits. So if suppose it is a 0 gate, it will be converted to a 1 gate, and vice versa. And it is being denoted by the matrix like of 2 cross 2, 0, 1, and 1, 0. And this is the gate symbol for the poly X gate. So if suppose we are designing a circuit in which we have to convert a particular information to, or we have to negate a particular information, then in that case we will be going for the X gate. Next one is Hadamard gate. It puts a particular qubit into, I mean, in a state equal to the superposition, and it is given by the matrix of like 1 by root 2 and into 1, 1, 1 minus 1, as you can see here. Okay, and H is the basically symbol which is used for denoting the Hadamard gate, H gate, basically what we call as. And next is C0 gate. So C0 gate, what it does is, like, if suppose, I mean, it basically acts as a like XOR. If control is 1, then it will flip the target qubit. Okay, or else it will keep the, I mean, suppose if we have 0, it will be 0. If you have 1, then the bit will be, I mean, 1 0, then after it will be 1 1. I mean, only in the state when both the qubits are not in the same state, then it will be the same here, as you can see. And if the second bit is like 0, it will be 1. And I mean, for any of the 1 kit, it will convert the target bit. So here the control is with the 1, then the target bit has been flipped to the 1 and 0 here. Since we don't have control 1 here, that's why the target bit has not been changed. Okay, so this was just a basic introduction to a few of the gates. Now coming to the Qiskit. So Qiskit is a framework which was designed by IBM, and it has 5 elements. So it works basically as a software development kit for directly interacting with the quantum simulators or actual quantum computers existing on the IBM clouds, which they have provided openly for the community, and anyone can go and code there. And if someone is willing to contribute to the Qiskit, I will share the GitHub link also, where you can go and contribute and improve the existing code or repository, or you can contribute for any of the algos, whatever you're thinking of. This Qiskit framework has been released under the partial license 2.0. Okay, so if we talk about different elements of the Qiskit on which it has been built, so it has 4 basic pillars like Terra, Ignis, Aqua, and AR. And so Terra basically is responsible for interacting with the hardware part, where actual circuit designing and execution of the code happens. Okay, and just for the information, Terra, this word was derived from the Latin word, and which means the earth element, which is the foundation for all of the other pillars of the Qiskit, like Ignis, Aqua, and AR. So basically, whenever we will be working using any of the sub-framework of the Qiskit, like Ignis, Aqua, AR, they will be processing the code and they will be sending it to the Terra, which is used for interacting with the hardware directly. So Terra defines the interfaces for a desirable end user experience, and it handles the layer optimization, scheduling the pulses, and all the backend communication happens using Terra. Okay. Next is Aqua. So Aqua was derived from the, I mean, we all know Aqua is somewhat related to the water. So Aqua was is used for the water element, which is another element of life. And this is which is, this is basically used to find the real world applications. So the algos like which are used for reducing the noise in the existing environments and all are being implemented on Aqua. And here we build the applications for the quantum computing, like in several other domains like chemistry for optimization, or in the field of AI and machine learning. And even people are developing algos to run neural network models on a quantum computer. So such kind of applications are being built on the Aqua. Okay. Next is Ignis. So Ignis is basically the fire element, which is totally dedicated to fight the noise and errors in the path of, whenever we are going to run some code, so there will be some noises and errors caused by the environment or any of the faulty method. So to tolerate that, we have the Ignis. What it does is it better categorizes the errors, and it improves the gates, and even it reduces the noise level while making the computation. So suppose there's someone who want to design quantum error correction code, or who wish to study ways to characterize the error through different methods like tomography or using some gates, then he can look at the Ignis part of the Qiskit. Okay. Next is Qiskit Air. So Air is the it has been taken from the air, I mean which is existing in the environment, and that is the another pillar of the Qiskit. And this is basically used for speeding up the development of quantum computers. And because each time whenever we are designing some circuit or we are planning to execute certain code on the quantum computer, on actual quantum computers, if we will directly go and run, it might can cause problem, or it can be computationally very heavy, and unnecessarily that computation power will go in states just like that. So before running our actual programs or circuits to the quantum computers, we can run that on simulators and check whether it is working fine or not, and then we can make it run on the actual quantum computers. So air is the framework basically which provides the simulators and debuggers to interact with the Qiskit. Okay. Whatever topics I'm covering, meanwhile, if you have some doubt, you can ping me in the chat box. Okay, so I will try to take it up.
Sadab, I am covering. You continue. No worries.
Okay,
If
sure.
that is a question specific to Qiskit, I will transfer to you. Till then, you can continue. I will take care of that one.
Yeah, sure, KG. Thank you.
The people are actively asking questions. I'm answering.
Sure. Thank you so much, KG.
Okay, Sadab.
Yeah. So that is what AR, air part of the AR element of the Qiskit does. Okay, so if we see a broad structure of all these four elements, how they are being implemented and getting used. So from this picture, you can see Terra is the basically element which directly interacts with the hardware. Aqua and Ignis are built on top of it. Aqua is built on top of Terra, which which is used for building implementing applications on quantum computers. As you can see, like for implementation of several algos like growers and all, VQE, or to implement machine learning algos like SVM version of machine learning algo as a QSVM. SVM is basically stands for support vector machine algos. So implementing such algos on the quantum computer, first it gets processed in Aqua, and then it comes to the Terra for better processing and getting directly implemented on the hardware. And air is the simulator which we can use. And then we have several areas of applications. As you can see, chemistry. In chemistry, you can mimic the structure or behavior of a particular chemical atom. Like suppose if you want to study hydrogen atom in detail, you can mimic the same structure in quantum computers and study about it. If you are going for AI field, then AI field implementing several machine learning algos, like for classification, we can go for SVM, and even developing or implementing the neural network models on quantum computers. And AI has because of the high computational capabilities, we are seeing a good growth in the field of finance as well. There are several algos which are computationally very heavy. If implemented properly on the quantum computers, that will be very much optimized and faster. Because while trading and all, even a fraction of seconds matters a lot. Okay, and then we can optimize certain problems. And even that is domain specific. Next is like Qiskit, Terra and all, like we have already spoken about. Okay, and about Terra, just to cover up the stack, this is how the stack of the Qiskit Terra looks like. So the user will give the input. The input can be circuits or schedules. And if you're directly going to work with the Terra element of the Qiskit, then that will be passed to the transpiler where the optimization and all happens. And the providers can be like IBM Q or any of the third party. And then finally, like visualization and quantum information tools are there using which you can plot histogram or get the states or get the entanglement done. Okay. And then Aqua also we have discussed. So just to have a overlook on the stack of the Aqua, here we define the applications we try to implement on quantum computers using Qiskit Aqua translators. So whatever input will be given, like that will be specific to a particular area, domain, or algos. And that application will be using some of the algos here, like whatever has been implemented or whatever you try to whatever you want to implement. Then those algos or those implementation will be again passed to the Terra, where the circuits will be compiled, and the final output will be given by the provider. So providers are again, IBM Q is basically the fifth pillar we can say of the Qiskit framework. 4 pillars we have already seen, but to directly interact with the quantum computers, IBM Q is quantum experience is the one using which you'll be getting the interacting with the Qiskit framework and actual quantum computers live. Okay, so just to get an example of the applications which can be implemented, we can see like if any of the bond structure you want to study, like bond of lithium and hydrogen, then what are their behaviors and all to mimic such nature in the quantum environment, that is now possible using Qiskit Aqua. And similarly in AI field, we can train any of the models and get the output. So here we have taken a classification problem example. So suppose if we have a data set, for example, if for a disease of uh, breast cancer, people who are suffering from that. Okay, so in that case, if you want to build a classification model that you can implement on quantum computers using AI machine learning algos, which have already been developed on a few of them already been developed on quantum on in Qiskit, and you can get the results. And optimization like max cut problem and all, those can be also implemented on quantum computers to optimize the overall configuration better and to find an optimal configuration. Okay, and then Qiskit Ignis stack is like list down all the quantum circuits of pulse schedules that will be passed to the, again, Terra element of the Qiskit, where the circuits will be compiled, and then the final output will be given using IBM Cube. So you can even plot the results using, so Qiskit has also the capabilities to give you the results in the visualization form. So they have the visualization tool as well. So if you want to plot any of the circuits, how does it look like, or what is the output of a particular circuit which you just executed, then that can be also plotted and visualized. And this is the stack of AR, where we are not using the actual quantum computers. Instead, we are using the simulators. So your input quantum circuit will, whatever circuit you have designed, that will be passed to the Terra, and Terra, based on the framework which you're calling from the Terra, that will call the, we have the option whether we want to use the actual quantum computers or simulators. Then if you are calling the simulators, then simulators will be called and your circuit will be executed on it. And from the backend, you will get the results, whatever you're looking for. So there are several kind of backends which are there for simulation also, like Quasar, state vector, and unitary. Each of them have their own significance and use. And meanwhile, like this picture is quite old. I took it from internet, and there's a lot of research happening in this field, and people are trying to come up and solve various existing problems in the for the quantum computers. So in the past few years, if you have seen, the growth around research work in the quantum computers has been increased rapidly, and even universities and schools are now ready to offer course content and research work, and there's large amount of research funds being granted by several fellowship institutes, research grant funds, which people are using to do the research in the field of quantum computing, quantum machine learning, noise, improving the noise errors in the existing in the quantum computers, optimizing the for the optimization algo. So you can imagine like how big this change are going to be for us, and and for computation. So for Qiskit, if these are the certain stats, like in the world so far, like there are 100K unique users and 6 million experiments have been done so far, and 130 scientific papers have been published across the globe. And this number would have been increased. This is the quite old data which I have picked. Recently, this number will be quite high than what we are seeing. And you can see like in what all region the IBM quantum experience are present, and what is the number of qubits which they are providing from that particular region. So as you can see here, it is 5 qubit, and for other regions there will be the number of qubits which they will be providing on the quantum computers will be different. Okay. Yeah. So there are many companies, startups who have already been pitched. So a few of the big companies we already know, like IBM, then Microsoft recently started with the Q-Sharp SDK, then Honeywell, D-Wave, Rigetti and all. There are other startups also who are providing online platforms. They are building they're developing quantum softwares. So if from software and consultant points of, if we see that category, then these are the certain companies like QCware, Horizon, and Q Branch and all who are working in these areas. If we see from the point of like the companies who are actually developing the quantum computers, then these are like IBM, Google, Microsoft, Rigetti, Honeywell, and Alibaba Group. So even Google also integrated the quantum framework with TensorFlow. I mean, now you can use you can program quantum machine learning algos on using TensorFlow as well. So that was being released by Google a few months before. And IBM has already its Qiskit. Microsoft has their Q Sharp, and there are several other frameworks available as well, like Penny Strawberry, and all. And from technology's point of view, like these are the major companies who are designing search circuits and providing the hardwares, like Zurich Instruments, Intel, and all. So there are several funding ventures also who are, I mean, providing the funds to the companies to take these startups to the next level. Like you can see we have Creative Destruction Lab, Quantum Valley Investments, and all, and there are many more. I mean, these are just few which I got from the Quantum World Association website. Okay. Yeah, so this was from my part. Now coming live to the actual Qiskit thing. So to run a program on actual quantum computers on simulators, we need to set up an environment. So, I mean, if you're going to run something from your environment, then you can install Anaconda software. I know many of you would be knowing. For those who don't know, you can go to anaconda.org or com. Okay. And there you can go to the, so download Anaconda, and based on your machine, you can decide like which version you want to download. Like, for example, I have, I'm using Mac, so I can install a 64-bit graphical installer or command line installer. If someone of you are using Windows or Linux, you can go for any of this particular version and get installed. So once you have Anaconda installed, so when you will, can you all see my screen, by the way? Can you?
I believe that all of the attendees are seeing.
Anaconda.com.
Yeah, menu icons are available or not?
Yeah.
Okay.
Yeah.
Okay, fine. Then you can search for the Anaconda, and you will get an icon like Anaconda Navigator. And using that, you can start the Jupyter Notebook. Or another way is you can open the terminal, and in terminal, you can type Jupyter Notebook to start that environment. I've already started. So if you will scroll up, you can see this is the command which I gave to the command terminal, and it will start a server locally for the Jupyter Notebooks. So Jupyter Notebook is the interactive environment, you can say, where we can develop the notebooks and write down the codes and all. Okay, so suppose if I have to create a notebook, I can go here. So this kind of ID you can get, and you can start coding in this. So before starting coding on the quantum computers, we need to install Qiskit also on our local computer, right? So to install Qiskit, we have a command pip install Qiskit, and that will install the Qiskit on your system. Fine. Another thing is, yeah. So if you don't want to do this setup locally, you can directly go to the collab.research.google.com. There also you will get a same environment like Google, and here you can create a new notebook and start writing down your code. Here also you can install the Qiskit. Okay. So once that has been installed, yeah. Suppose I did pip install Qiskit, it is done. Yeah. Fine. Then next what you can do is, let me start with this. Yeah. So once it has been installed, you can do import Qiskit. That will import that current package in your environment. So before starting with the actual coding on the Qiskit, I will also give a touch, I mean, how to get the APIs and all. So IBM has a website. If you will just go for quantumcomputing.ibm.com. I'm getting quantum computing India. Okay. This one actually. Okay, so this is the website where you can reference, and here you can create your account. So I will start showing you from scratch. So when you will come to this website, you can see this is just built for Qiskit and quantum computers. So you can either sign up or log in using your IBM ID. Since I have already my ID, so I will just log in directly. And once you are into that environment, sorry, my net is a bit slow. Okay, once you have been logged in, then you can go to my account, and from there you can copy your API token, which we need to run our code on actual quantum computers. Without that, it won't be possible. So you have to go here, you have to go to my account. Okay, and from here you need to copy your API token. That I will tell you where you need to paste. Okay, so before, and here you can even go to the circuit composer, and there will be several gates and all available for you where you can design your own circuits like this. So this is the circuit composer environment provided by the environment, where you can select the gates like H gate, X gate, Y gate, Z gate, and you can see we have many other you can design your own circuit. Okay, yeah. And we have starter notebooks also provided by the IBM itself. So you can go to this page, Qiskit notebooks. There you will get down a list of tutorials which were being prepared by IBM. So if you're just getting started with it, you can refer any of these. And they have a Slack channel also which you can join. If you have any issues with the code or bugs, you can either interact with them there, or even you can ping us also in the group. I mean, if someone from the community is willing to answer or from us, if someone is free, they can answer it down. Okay, meanwhile, it's loading. By that time, I will just import few of the packages, and I will show you like how the circuits are getting designed. So instead of using Qiskit dot, importing something using something like Qiskit dot and a particular function, I will import everything from Qiskit, whatever is available there, using Qiskit import star. And then I'm going to create a quantum circuit, okay, acting on a quantum register of 3 qubits. So for example, I can name it as circuit 1 equal to, and for that we need to call a method quantum circuit, and then you can pass the number of qubits I mean you need here. So since I need 3, I am passing 3. If you need 2 or more, you can pass the values as it is you want. So my circuit has been created now. Now suppose if I want to initialize, I mean each of the qubits which have been initialized, it won't be having any value, right? So I have, I mean it will be having, I mean a 0 value in that only, right? So if I want to apply any of the gates on that to change its state, or to make it into the superposition state, or to flip the bits using CX gate and all, using on control qubit, then we can do that. So first what we are going to do is we are going to add a H gate on qubit 0. So 3 qubits we have. Now we are going to design the circuit. What we are doing is we are applying hammered gate on qubit 1. Okay, so that gate will be applied. Now what we are going to do is, with the control qubit 0 and the target, I mean qubit 1, I mean we have 3 qubits, like you can understand it like this: q0, q1 and q2. Each of them are 3 qubits which we have initialized while creating the circuit register. Now on qubit 0, I have applied hammered gate. On qubit, now I'm going to apply the, for example, you can say C not gate with the control qubit as, with the control with qubit 0, and the target qubit will be 1. And then after that, I'm going to apply another C naught gate on control qubit 0 with the target qubit Okay, so I will tell you like what is happening at each of the stage. So when I'm applying hamlet gate on a qubit 0, in that case, my first qubit will be put in the superposition state. Fine, as I showed you on the slide, like hamlet gate are used for putting the qubits into the superposition state. Now, once that qubit is in the superposition state, then by applying C naught gate with the target qubit as qubit 1, I'm putting that qubit in a Bell state. And then when again I'm applying a C naught gate on the qubit 0, in that case I'm putting that, you can say, qubit to the GHZ state. So GHZ, who don't know, you can just see it is Greenberger Horn Zillinger state, and I'm not going to deep dive in it. I mean, again, it will be too much physics here. So just for information, you can just get to know. Like here, we are putting it in Bell state, and similarly, again, we are applying this, and the target variable will be target qubit will be 2, and this state will be GHZ state. Fine. Now my circuit is ready. I chose 3 bits. I applied certain type of gates on at each step. Now if I have to visualize my gate, I can use draw method of the Qiskit. So using draw, I can pass the parameter ampl, and using which circ1 is not. Oh, sorry, spelling mistake. You can see this is how a circuit looks like. So whatever circuit you're designing and whatever operations or gates you're applying on your qubits, those you can visualize that as well in Qiskit. So here what I did, applied H gate, then applied C naught gate for converting it to the different Bell state and GHZ state. Okay. So similarly, I mean, if you want to code something on, I mean, this is how you can visualize the framework. Okay, and now suppose if I have to use the simulator which is being present as a part of the Qiskit, then for that we can use from Qiskit import AR, and that will basically import the simulation all the simulation functions and method whatever we have in here, and using AR dot we can call it. So if I have to get a backend for that, so each of the quantum circuits and code, whatever you're going to execute, will be running somewhere at the backend. These backend can be either simulators, or these backends can be actual quantum computers existing somewhere on the cloud. So we need to, I mean, pass that backend name, like using what we want to create a backend, and on where we are going to execute our jobs or circuits. So I'm going to use state vector simulator for now. So air dot get backend, and in this I can pass my simulator like state vector. We have seen there are several simulators present as the part of the air, right? So and yeah, so I have got my backend. Now if I have to execute this circuit which we have created here, I need to call execute circuit name and then the backend name, and this I can store to a variable job. So now my circuit has been executed. Okay, now after execution of the circuit, there will be several parameters which will get assigned to the jobber. So suppose if I want to see like what was the result of the circuit which I have just executed, I can call result method of it, and that will give us the output of that particular circuit which has been executed. So that this I can store in the result. Okay. Now, since we have executed this on a state vector simulator, to print out the output and up to what decimal levels I want to check, what I can do is result dot get underscore state vector. I mean, for the first time it will sound something complex, but once you will start with it and following the tutorial, that will become easy for you to go. And suppose for decimal values, up to decimal values 2, I want to check it out. just a minute. Qiskit dot result has no attribute. Actually, result one, it is right. Sorry. So you can see the output has been given in the vector form. I mean, for each of the state, we have several values, and these are the complex numbers. Basically, it won't be existing in the real number forms. So there's one real part and there's one conjugate part of it. Okay, and now if you want to visualize your results, so let's store this in another variable. And if I want to have a look on like what has been the output from that circuit, I can use the visualization tool available in the Qiskit like. So plot state city is one of its functions. There are many other functions which you can use. So I can call this function and I can pass my data in it, which was output 1. And yeah, so here you can see like how you can visualize the output, what was the real part, what was the imaginary part, and so on. Similarly, you can even call other backends like unitary backend and all. Okay, so unitary backend can calculate matrix up to 2 cross n into 2 cross n. And state vector backend can handle the vector of dimensions 2 pi power n, and where n is the number of qubits here. So for state vector, it is 2 pi power n, and for unitary backend, it is it can handle the matrix across 2 cross n into 2 cross n, like that. Okay, so I will not go deep into unitary and other simulators available on the quantum computer. I will now show, now we will execute some code on the real quantum computers, I mean, by passing our key. So for now, for example, suppose this is the code, right, which I can remove from here. And yeah, so for importing that, as I have told, like for creating that, you can say, for running the code on the real quantum computers, we needed a quantum key from here, and that you can copy and paste that in the notebook, which will help you in running the, I mean, which will be the key for running your codes on the actual quantum computers. So instead of going there, we can directly, let me see. Yeah, so let's come back to this notebook. So for that, we need to import the aqua from the Qiskit, and then we can start coding for that also. Okay, so before going forward, I mean, if you want to check the version of the Jupyter notebook and all using, and what are the different version of the frameworks or the elements which is getting used here. So you can import this thing, qiskit.tools.jupyter, and then you can print inline using the magic commands, qiskit underscore version underscore table. And so this will give you the all the versions of the framework being used here. So you can see right now on my system, which has been installed, the version of Qiskit is this, Terra and all. And this is my system information, which will be taken from the my system. So same way, if you want to check for the system information as well, you can go for that. Okay, yeah. So now we have already Qiskit imported, right? So import. We have already imported Qiskit like this. Now suppose if you want to use your API token and you want to run your circuits on the actual quantum computers, you can call Qiskit. First, you need to save your account on the disk so that whenever you are running some code on whenever you're trying to run some code, you can just directly call it and you can use it. So ibmq.save_account. This will save your API key on your local disk, and whenever you will call, that will be able to execute your code on the actual quantum computer. So I need to copy the key again. Yeah. Sorry for that. Yeah, coming back. Why this is not going? Yeah. I can paste my key here. Suppose if you've already saved some key and you want to override the existing key, then you can just pass overwrite is equal to true in that case. So that will override the existing credential for you. Okay, once I have that key in my environment, then I can load, I mean, we can check out like which all providers are available on IBM cloud environment. So you can just run the command like dot IBMQ, and then you can load a list of all the accounts here. And then by calling the backend method on this variable, you can get a list of all the backends used. So you can see a list of all the backends which is available to us using IBM Q account. So we have a simulator also, and we have actual quantum computers existing in several regions like Melbourne, Vigo, London, Wellington, Essex, Rome, and all. Okay, each of them are having limited number of qubits processing capabilities. So that if you want to check, you can go to the dashboard, and here you can see like IBM Q16 means this Melbourne quantum computer can process 16 qubits at a time. No, 15 qubits actually. IBM Q16 is the name. 15 qubits it can process, 5 qubits here. And for London also we can process up to 5 qubits. And using Q, I mean, this indicates like what is the execution load on each of these quantum computers. So there will be many people across the globe who will be executing their circuits and codes, right? So this will help us in identifying that. So once we have a list of all the backend providers, we can check for the backend which is very least busy. So for that, we can call Qiskit dot providers dot IBMQ dot least busy, and we can pass this list here. Okay. Now, while passing this, suppose if instead of using the simulators, you want to get with the quantum computer backend, which is least busy. So here you can pass an argument, simulator is equal to false. Okay, so that will only give output name of the actual backend, which is least busy. So if I will print backend here, backend.name. So it will take some time because it will try to get the execution load on each of the quantum computers, and then it will give you the output. So we can see for OU Rens region, this one, we have the least load on that. Fine. So let's do one thing. We have already a circuit designed. So what we are going to do is we will create a new circuit to execute that on quantum computer. So since we don't have enough time, I will try to wrap it up quickly. And here we can create a register, and then we can use a classical register to get the information, to store the information. So using quantum register, you can create the qubits. Using classical register, you can create the classical bits. And here also I will use one classical bit. Let's create a program, and that I'm going to, for that I'm going to create a quantum circuit. And here I can pass these parameters, classical qubit as well as the quantum qubit register. Fine. And at the end, what I'm trying to do in this program is I'm just trying to measure the value of qubit into my classical bit. Okay, so I will just measure my qubit and I will write down its output to the classical bit. So first parameter will be the qubit name, which I want to measure, and where I want to write will be the second parameter. So this qubit will be executed, this circuit will be created. Now we have to execute that circuit. So for that, we can call qiskit.execute, and then we can pass the program or circuit name, and then we can pass like, where do I want to execute this? So we have already seen like on classical bit on simulator how it works. Next, we are going to execute this on the actual quantum computer. So what I will do is I will pass program, and backend I've already updated. So I will use backend here. Now this whole circuit will be getting executed on this quantum computer. Now this job has already been executed. Now if you want to see the result of this job, we can do job.result dot. We can get the count. So since we had zero value in that qubit, so most of the time when this qubit will be measured, that time the number of zeros will be high, and because of the existing error in the environment, there will be few chances when that qubit will be measured as 1. Okay, so you can see this experiment will basically by default run for 1024 times whenever we are executing this. If we want to run it more time or lesser time, you can specify that in this. So this, after executing this statement, you can see approximately 1000 times the qubit was measured correctly, but for 17, close to 10 to 15 times, it was measured wrong as well. Okay, and similarly, we can create the entanglement also on the quantum computer. So we need to create 2 qubits here. I mean, we need, wait, let me copy this code here from here, and we can use the existing code for creating the entanglement. Okay, so for entanglement, I'm going to use, we need 2 qubits. We are going to mimic the behavior of one into another. And similarly for storing their information, another 2 bit of classical bits. And then we can create a circuit like this. And as we applied several gates like H gate and then C naught gate and C naught gate, the same way we can apply the gates to get the quantum circuit into the qubit into the entanglement state. So what I'm going to do is, instead of measuring, I'm going to apply first H gate that will put that into the superposition state. And then we will apply C naught gate on this. So the control will be with qubit 1 that we will be measuring in. That will be transferring to the classical register basically from here. Okay, and then we will try to get its value. So we will measure it up, and then here I have missed QR. Yeah. Done, and then after that I need to execute my circuit. So for executing, I need what? Pass the program name, then pass the backend and number of shots you want to give it, like how many trials do you want to get it tested for, and like you can even specify like max credits to be used or not. Okay. Okay, so in CX here I did here it should be we are applying as a CNOT gate from qubit 1 to qubit 2 actually. So it will be QR1 here. Fine. So once the job has been executed, if you want to see the circuit, you can call program.draw, and that will display the circuit which has been executed on the actual quantum computer. So you can see like we applied H gate, then we applied a C0 gate from qubit 0 to qubit 1, and then we measured the values of both qubit 0 and qubit 1. Fine. For measuring, we need the classical bits here. So this is how we can do now. Whatever we have done, if suppose if I want to visualize my results, like how many times it has given 0 and how many times it has given 1, then I can plot the output as a histogram also. So I will call plot histogram method of this, and then in this I can pass my data, which is in job 2 dot results, and we can get the count of each of the qubits on the classical register. And for that, I need to pass the program here. Fine. Yeah. So this was the last part from my side. You can see like how many times the qubit has been calculated as 0, how many times it has been got as 1, 1. So 0 is for the first qubit, and another is for the second qubit. So how many times it was actual 0 and got 1, how many times it was actual 1, it got 1, and how many times it was 0 but calculated as 1, and how many times it was 1 but got calculated as 0. So these are the certain probabilities of the outcomes here which we had. Okay, so that's it from my side, and thanks for being online. This is the first entanglement which we have created on the actual quantum computers. Before, what we did was on the simulator here. Okay, so any question? I will open my chat. Let me go through it.
Yeah.
Yeah. So question from VK is like, which library is good to start with Qiskit? Qiskit, PyQL, I mean, see, every package is good, but since Qiskit has good community support and it's getting widely used by the members and those who are getting started with the quantum computer, as well as it is being widely adapted with the researchers also. So Qiskit is good to go. I mean, just for the starting, and even it is built on the it is using Python. So Python is basically the easy language for the people to learn and start programming. Okay, anything else I have left out? KG, it seems most of the questions you have already answered. Yeah. Yeah, so any specific question I have, you can just ping me in the chat. I mean, we can take up 2 to 5 minutes more, and then probably Sam can give a thank you note. Yeah, thank you. Then over to you. Thanks everyone for joining.
All right. Thanks, Shadab.
Yeah.
Guys, like this, like we keep saying, this is the beginner session, so don't get intimidated. If you didn't understand anything, just join us. That's all, right? Like we'll keep doing this. So a couple of things, just 2 things. One, the website, it's quantumcomputingindia.com. Just check it out. And the most important thing is the feedback, right? So I'm just putting a feedback link over here on Zoom chat. Please spend like 3-4 minutes. That's all it's gonna take. It'll help us structure, more events like this, or you want like an advanced level and stuff like that, right? And the website is quantumcomputingindia.com. Right, yeah. Cool. 1 second. All right, so we have like different tiers of membership. So of course, there's a free tier. You can just join us, be part of our open WhatsApp and Telegram groups. And if you want to be engaged at a deeper level, there's like two more levels. One is a bit level and qubit level. You know, for lack of creativity, we just used the quantum terms. Um, yeah, and then like every other detail is on the website. Like we'll be coming out with courses as well, so we have like workshops planned and just like specific to mathematics. Then of course like podcasts, like all those three tenets are still the same, like the knowledge series, the hack series, and being part of the community. um, I really suggest that you become part of the hack series, because that's when we really learn, right? Because like all these things looks interesting, like, but then like when you really try to apply it, that's when learning happens, right? Yeah. So with that, the feedback form is the most important, because that helps us know where we stand in terms of our delivery, in terms of like pre-event communications, and what kind of events that we have to do in the future, right? Like we'll keep conducting this, like, free open sessions for like the general public to know about quantum. It's in a very early stage. But like I keep saying, the hack series is where like real like fun happens, right? uh, and like these are people, professionals working elsewhere, coming together to create something, and the process itself is very interesting to just watch and be part of that. All right, so with that, thanks a lot. It's Saturday, like almost 2 hours and 5 minutes you guys have spent with us. I hope that was useful, and it like piqued your interest in terms of pursuing your career in whatever field, right? Like business, cryptography. If you're interested in cryptography, part of things, just like reach out to me. Um, and breaking down of research papers is another thing. Like few of our community members, like Sayantan, I'm not sure if he's here. Like Sayantan has already released a paper, so soon we'll have a discussion with Sayantan about the paper that he has done. Yeah, it's like generally a great way to be in touch with people who are excited about the same technology as we are. And then like this collaborative learning is a great way to keep learning and keep pushing ourselves further. Incidentally, KG, Shadab and I, when we first met, like KG said that like he thought about this, like starting something very similar to this like 10 years ago, right? For him, it has taken 10 years to realize that. But yeah, I mean, like it's better late than never, right? Yeah, Ivan, yeah. We really learn a lot from that, right? Because like 3, 4 of us sitting together and just reading the research paper and then plugging the gaps together. If you want to be part of that, yeah, please, more than welcome. And Australian research is something that we are watching very closely. Oh, and one thing that we do, if you're in Bangalore, we do this walks in IISc. Like we go to IISc, we see the research that happens over there. That's something that we had planned in April, but of course it didn't happen. But once this relaxation happens, and then like people are allowed to move a little more freely, we will organize that trek, a quantum trek, if you want to call it that. Really, really cool professors who are working there, and they're doing insane stuff. Yeah. And like few of our community members are working with the professors now. They've gotten internships, apprenticeships. So yeah, just be part of a community that, where you can like thrive. That's very important. All right. Feedback form, check out the website. How to know about the ISC event? Yeah, we'll let you know. So if you're part of the meetup group or WhatsApp, the open WhatsApp and Telegram groups, you'll definitely come to know. Yeah, we haven't decided the time yet. Yeah. All right, thanks, Shiva. All right, that's it from our end, guys. Like if you have KG, do you have anything else to add?
No, sir. All good. Thanks.
All right.
Thanks for all.
Thanks, Shadab. That was really, really, really fast, but really good. Yeah.
Yeah. Thanks, everyone. Bye.
Link to what, Tamal?